What we're going to do now is plot the conformations of butane on an energy diagram. It may not be entirely easy to see, but I cleaned up our previous slides so we have reference points to look at. And we're going to go from the 0-degree dihedral angle all the way up to 180 and then back to 0. So what that means is our starting point is actually going to be this conformation right here. And so we can keep track, maybe I'll give each of these letters. So this will be A, then we'll go to B, C, D, E, and F. Okay, so let's plot A on this diagram. We're at a 0-degree dihedral angle. The relative energy, and I should include energy values on my y-axis. So we have our y-axis now from 0 to 5 kilocalories per mole. We're going to start at the 0-degree dihedral angle and find where we'll plot conformation A, and that'll be at 4.6 kilocalories. So I'll put a dot right here at about 4.6 and label that as conformation A. Next, we go to conformation B, and that is at 60 degrees with a relative energy of 0.9. So I'm going to put a dot just less than 1 for conformation B. Next, we go to conformation C. That's at 120 degrees, and the relative energy is 3.8 kilocalories per mole. So I'll put a dot here at about 3.8. That will be C. We then get to conformation D. Conformation D has a 180-degree dihedral, so it'll go here, and the relative energy of it is 0. So I'll put a dot right there on 0. It's D. And then from there, we're actually going back to a 120-degree dihedral for conformation E, which falls at 3.8. So there's E. And then for F, we go to 60 degrees, and that has a relative energy of 0.9. There's F. And then you can actually continue, and what we've done, we're back at A, and I'll go ahead and plot A again at 0, which is 4.6. From here, we can connect these dots to come up with an energy profile. So if I start at A, go to B, go back up to C, down to D, up to E, down to F, back up to A, and then we continue. So what we have here is a series of local minimum and local maximum. So we can say that conformation A, well, we can say that A, C, and E are all maxima, and B, D, and F are all minima. And globally, A would be the global maximum, D would be the global minimum, in this case, the lowest energy conformation. So one reason this is useful is because what we've done is we've just looked at the conformations of the extremes. But as I said before, there's an infinite number of possible conformations. So what you can do is predict a relative energy based on the dihedral angle. So for example, and you can do this much more accurately on a computer, but let's say I wanted to know the relative energy at 90 degrees, which would be about right here. What you can do is trace up and find the energy at 90 degrees, and that a 90-degree dihedral looks to be about maybe 1.7. And that's a rough estimate.